Hello, everyone. Welcome back to AAS Publishing, and this will be one in the author series. And I'm delighted today to have Bożena Czerny with us, who's going to be talking about one of her papers. Hi, Bożena.
Hi.
Where are you at?
Well, should I present myself generally? Well, first of all, I'm in Warsaw, Poland, and as you can hear from my pronunciation, I'm not an English person and not an English speaker, but I try to do my best in this language because this is the official language of science, right? And I work at the Center for Theoretical Physics right now, Polish Academy of Sciences. So I do not teach, but I do research, and my research mostly focuses on active galactic nuclei, not exclusively, but let's say mostly. And for 4 years, I was mostly interested in what is happening very, very close to the black hole. But recently, I decided to change a bit, to get some distance from the black hole.
Okay.
And started to be interested in the broadline region, with radiation emitted at few hundred or few thousand gravitational radius, so quite distant. On the other hand, the issue is quite important because the most characteristic property of active galaxies are strong and broad emission lines. This is how quasars were discovered in the first place.
Right.
So I started to think how it happens that this material is there ready to be irradiated by the energy generated very close to the black hole. And then I came with a new model, which was developed by me and my graduate students already a couple of years ago. And I was quite happy with that model. So I decided to pursue the model observationally. So I started doing observations for the first time in my life. I'm not very young, as you can see.
It's all staying.
In 2013, I decided to apply for observing time with large telescope. I never did that before. I never did any observations before because by education, I am a physicist. So I never used even 15-centimeter telescope, and still I applied to use 10-meter telescope. And my main motivation or encouragement was that I don't have to go there and use the telescope because I was afraid that I will destroy the telescope and it's pretty expensive.
Well, you haven't, so you're still.
Well, but fortunately in that case, observations were always done in remote, service mode.
Yeah.
I never actually saw the telescope. On the other hand, I'm a good theoretician, I think, so I wrote a good proposal and it was accepted. And for the last 6 years, I collected the data.
That is cool. Very cool.
Behind the paper we will talk about today.
Speaking of, let's get to the paper. And just one other point for those who know, Bożena also happens to be a scientific editor for the AAS journals, but that is another topic that we will talk about perhaps at another time. So let's go ahead and walk through your paper, and this will be the time delay measurement of MG2 line in CTS C30.10 with salt. So Bożena, take it away.
Okay, so the project, as I already mentioned, was a long-lasting one we started doing it over 6 years ago. Why for so long? The aim was to measure the size of the broadline region, and the size of the broadline region is measured by the time delay between the emission generated close to the black hole and the fact of production of emission lines. And the size of the broadline region in distant bright quasars is just large. So we expected the time delay of order of 600 days, roughly 2 years.
Mm-hmm. Okay. So what is particularly interesting about CTS C30.10? Is it just easily observable, or does it have some unique characteristics? Why this object? Why this quasar?
It's bright.
Right. Awesome. That works.
When we started our campaign, which was 7 years ago, we had to select sources quasars which are bright. And there are not that many bright quasars. So we selected a few, and during pre-selection, we rejected 3 or 4 because they had some absorption, whatever. We wanted to have a nice emission line. But basically, the object is bright. The magnitude is 16.5. So this is really bright.
Yeah. Okay.
Our motivation was mostly observational because the SALT telescope is a large telescope. On the other hand, you cannot order long observations because of the construction of the telescope. Sometimes the object is visible only for 40 minutes and it's gone because the telescope does not follow the object. Got it. Yep. So that was the motivation for the large brightness of the source. On the other hand, we also knew that it will be very important because it's easier for the from the point of view of time constraints to model, to follow low redshift, intermediate redshift sources, but not so bright sources because the time delay is shorter. And we expected that probably soon somebody will do similar study for nearby, or for sources which are not so bright. And it did happen indeed. So our measurement of magnesium 2 line, when it was completed, it was not the first measurement. Okay. But nevertheless, this was one of the two brightest sources measured. So that was a nice change. Yeah, but so here's figure 1, which is an exemplary SALT spectrum. Yes, that shows why SALT was very, very useful for this study, because the problem with magnesium 2 line is that you don't see in that location only magnesium. You have also underlying power law, continuum, which is kind of obvious. Right, that's the green. But that's the green thing here. But what is more important, you have also the contribution from Fe2 emission. And this is this dotted blue line. Mm-hmm. And Fe2 emission originates more or less at the same place, maybe a bit more distant. So you have to be prepared for the variability both in Fe2 component and in magnesium 2 component. And you have to decompose the spectrum reliably. Otherwise, you will measure something like the 2 at the same time, right? And you won't measure really the time delay of magnesium 2. And with smaller telescope, you cannot do this kind of decomposition. Cool. That was the advantage of using large telescope, and we were able to model the shape of the magnesium line pretty well. The magnesium line is clearly asymmetric, so we needed two components, those pinkish lines.
Right.
They both represent the magnesium 2 shape. Yeah. Question?
Yeah. Are those two? So on the pink lines, are those? Are they being emitted from different regions? So why is there two?
I don't think those are two different regions.
Okay.
Because we also tried to determine the black hole mass, and the black hole mass is usually determined either from broadband SED fitting, which we did, or from the line width. So we tried to use the line width of those components separately,
okay.
but did not give anything which would be comparable to what we got from broadband SED. So broadband SED fitting was consistent with treatment of the whole line as a single thing. And it's just that the shape is not symmetric.
Got it.
The broadline region apparently is not as perfect as we sometimes may think it is.
I get it. Got it. I understand.
Of absorption, whatever, but the composition is not hinting towards two separate zones. By the way, we continue monitoring the source. So in principle, with longer monitoring, we can independently try to measure time delay of those two separate components.
Yeah.
But I don't think that they will be different. I don't think.
Okay.
So then the goal of the paper was actually to measure this time delay of the magnesium 2 line with respect to the continuum. And to do that, we used several methods. The smallest error is obtained when we use Javelin method. That was this nice figure 9, I think, of the paper still
down, figure 9, okay.
Yes, this is the figure 9. So this is the advantage of Javelin software. Javelin software gives the final time delay concentrating on just one, the best solution for possible time delays. Other methods are not so selective, so then if you have to include other possibilities like additional 500 time delay, 500 days time delay, or any other thing, then the error is large. But what Javelin method does, it identifies the most probable time delay, and then focuses on concentrating on finding the peak in this distribution. So on one hand, it gives really fantastic accuracy, like plus minus 2 days or so. On the other hand, one can make have reservations about this achieved accuracy. So in our result, we actually combined several methods, and we calculated the average value which was obtained from many of those methods. And the result was in the observed frame just above 1,000 days, which corresponded to just above 500 days in the rest frame of the quasar. Quasar is located at redshift more or less 1.
So let me ask a question about the figure. Yeah, I see in the clean data the red, which is going to be the most probable. That's your 1068. Do you attribute any physicalness to the other times when there are signals. So for example, there's a little bit of red around 200. Is there something physical about that, or what do you make of that?
No, I think this is just that the number of observing points is not high enough to kill other possibilities.
Okay. Okay.
If we have 200 or actually 2000 spectra, I think we would have just one time delay. Unfortunately, you know, telescope time is quite expensive and we had 20 something spectra. So this is probably the artifact.
How much total time what was your total time on this object? On this run?
We had 25 spectra, and during those 6 years, and each observing run took about 40 minutes.
Okay, okay, got it.
So that's...
Very good. Okay.
So measuring this time delay finally allowed us to construct this radius luminosity relation, which is shown in this plot. Yes, now we can see that. So here, as I expected, somebody else will measure this time delay as well, and those blue points here sorry, I should say what is on those axes. So here you have a luminosity in the rest frame of the quasar measured at 3000 angstroms, and the vertical axis is the time delay. So those blue points were relatively recently measured objects from SDSS reverberation mapping project. Mm-hmm. And their observations lasted for half a year.
Oh, wow, okay.
They were only able to measure low luminosity sources. Our quasar, you see, is almost 2 orders of magnitude up. This is our source. And the only one which is even brighter is this blue source close to 47. This comes from Paulina Lira, and that was obtained by pure accident or actually a mistake of the authors. Because they did monitoring for 13 years, Paulina Lira and collaborators, but they aimed at carbon-4 time delay.
Okay.
And they somehow misidentified the redshift, and they included this source, and potentially carbon-4 appeared definitely to be magnesium-2.
Yeah, okay.
But having those 2 high luminosity sources really allowed us to construct this radius luminosity relation. Without those objects, you couldn't tell much, right? And this radius luminosity relation is very important because in massive surveys, you do not measure the time delay of individual objects because it's too time consuming.
Right.
You use just a single spectrum. So then you have the line width from a single spectrum, and then the radius is just determined from the luminosity. Okay. Because assume that the source is on that axis, and then you can calculate the black hole mass, and this is how black hole masses are calculated in large surveys.
Got it.
So that was done in such way for H-beta mass determinations. But when magnesium-2 line was used, it was just, people had to use basically the results for H-beta. Now we have the direct radius luminosity also for magnesium-2. So if you have quasars at redshift 1, this offers the solution to the black hole mass measurement. And then additional possibility, if indeed this radius luminosity relation works, it can be later used to do cosmology.
Yep.
That's not so simple, and the scatter is still a bit large. So our first attempts are not yet very successful. I mean, they do not give definite constraints on cosmology. But it's a promising alternative model, because if the object is measured by reverberation mapping, so this time delay is determined, then if this radius luminosity relation holds, then we can determine the absolute luminosity from the time delay. And if we have absolute luminosity and we have easily measured flux, then we can calculate the luminosity distance. And luminosity distance is what people in cosmology want, because luminosity distance depends on cosmological parameters. But that application is not yet fully ready. On the other hand, taking into account problems with Hubble constant and model tension, whatever, we look forward to get time delays for more quasars and see how this method will be doing in the future.
Very cool. So that sort of points in the direction of where do we go from here, or where do you go from here, given what you've published in this research. Do you anticipate getting more time on CTS C30 to knock down the error bars even more?
I still continue with this quasar, so I will try to determine also the time delay for Fe2 and separate time delays for those two separate components. I have also two other quasars which I started to monitor at the same time as CTS, but because of the weather constraints, I got a bit less of the data for those two objects, but one now is completed, analyzed, sent for publication. We have sent the revised version, so we are about to publish the time delay for the second quasar.
Cool.
And third one is in the process, but we still have to do to get photometry properly for the third one, because it's not only spectroscopy what is needed, it's also photometry. This is why the number of people on the paper is quite large, because a lot of things are actually needed to complete the work. So you can see that the list of authors is pretty long, because part of them completed photometric reverberation monitoring for us, different telescopes. And of course, data reduction is quite complicated, and it was done always when the data arrived. So a number of undergraduate and graduate students were also involved, and they were coming and going away, right? So
that's very cool. Very good.
That contributed to the number of authors.
Quite the international collaboration there too. We got Poland, Germany, Chile, Czech Republic. Very nice. Cool. All right. Well, thank you so much for sharing, walking through your paper with us. And feel free to go ahead and contact Bożena by email. We won't be putting her email in the YouTube description or in the video, but you will know how to contact her. Plus, she's also a AAS scientific editor, so she's pretty easy to find.
Yes, that's true.
Yeah, so feel free to contact her. And I want to thank everyone for tuning in and learning about MG2 lines in quasars. So thank you very much. Bye, everyone.